very much for joining us to hear about the Graduate Certificate in Internet of Things. As Anya mentioned, I'm the chair of this program. So I'm happy to be able to give you some further details about the program. I'm sure you've read the Springboard pages, and to answer any of your questions that you may have. So before we look at the details of the program, I just would like to briefly introduce Dublin City University and the School of Electronic Engineering, which provides the program, in case you're not already familiar with us. So DCU is a relatively new university. We celebrated 40 years in existence this year. And we've always had a very strong focus on industry engagement in both through our teaching and our research. And as you probably know, universities are ranked by various metrics, and we're very proud that one key ranking that has come out this year is that we're ranked 19th globally for graduate employment. So that really confirms where our drive has been in providing practical programs that are valuable for a student's career and are of high demand in industry. And I think that's particularly important for the Springboard program, that our programs are very targeted at industry and in furthering, helping you to further your career in this growing domain of IoT, which we'll speak about today. So the program is delivered by the School of Electronic Engineering in DCU, and we've a lot of experience in delivering taught postgraduate programs. We began in 1980 initially with a Bachelor of Electronic Engineering programs, and quite quickly through interaction with industry and our graduates, we realized there was a demand for a level 9 master's program, and we started our first master's program in 1990, and it has been running ever since. In addition to that, because of our linkages with industry and industry's demand for our programs, in 1997 we started delivering our programs in a very flexible remote learning mode as an option for students in industry. So we also have a lot of experience in delivering online programs right back to 1997. So I'll speak a little bit about how the program will run given the COVID-19 circumstances and how that relates to our experience in delivering programs remotely. So our programs are very driven by our research and development, which is our research, or rather our academic research. And our research has strong linkages with industry between the academics and the school and local and global industry. And that very much informs also our approach to teaching, so that the teaching, what we are teaching is state-of-the-art, advised by industries, not just current but also future needs. And we've found, through this approach that the skills and knowledge that our graduates come out with are then in very high demand in industry. So this program is about the Internet of Things, and the Internet of Things can mean different things to different people. It is a relatively new term, so I'd like to just define what we mean by Internet of Things, the full breadth of the term, and then how that relates to the course content and how we address what is important in this area. So we're all familiar with the fact that there's a huge growth and proliferation of what we might call generally computer devices. So smartphones, tablets, PCs, data centers with hundreds of thousands of interconnected machines, and so on. But maybe what is a little less obvious is the growth in what we call embedded systems at the same time. So an embedded system is a system that centers around a small single chip computer, which we call a microcontroller. So the difference between a microcontroller and a microprocessor that you get in your phone or your laptop or your tablet is that it is entirely self-contained. It has its own memory. It has its own ability to interact with the outside world without the large number of additional chips that are required to make a laptop, for example. So they're small, they're very low powered, and crucially, over the years, microcontrollers have developed to be interconnected so that they can interact with larger systems. So just to give an idea of the growth in embedded systems compared to computing generally. So last year, there was something of the order of 2 billion or 2.2 billion microprocessors sold. So most of those ended up in smartphones. At the same time, in the microcontroller market, the sales were something in the order of 25 billion globally. So the driver for this are the embedded systems that are being developed in industry to control industrial processes, in consumer goods as well. So we're familiar with the smart home concept, where you can control and monitor your home through your smartphone because there are microcontrollers, embedded systems in each individual device, switches, locks, light bulbs, and so on. But the microcontrollers are much more pervasive than that in the world. So, for example, in pharmaceutical manufacturing, to get efficient processes in energy, there's a huge number of these devices embedded with sensors to control the process. Modern cars have something of the order of 50 or 60 individual embedded microcontrollers, which are all interconnected, each one doing a particular job. For example, sensing exhaust fumes from a car and feeding that information back to the engine management system to improve the efficiency of the engine. So, given this proliferation of microcontrollers, which interact through sensors to the physical environment, there's a huge amount of data generated by these microcontrollers. So to compare it to the amount of data that flows around data centers, which was something in the order of 20 zettabytes last year. So a zeta is 10 followed by 21 zeros. IoT sensors globally combined, it's estimated that approximately 100 zettabytes, about 5 times as much data was generated. So obviously this information cannot be sent to the cloud, to data centers in its entirety for processing in order to analyze the data and give feedback to control systems. So a key part of IoT is when we connect IoT sensors to the cloud to do something useful. For example, you'd see that the image top right of the screen there is a drone. So a drone contains many microcontrollers, each of them individually connected to sensors to control the navigation systems and the flight control systems, the motors and so on. But that is networked back to a larger system that automates, that gives the drone a task to send a particular package, right, to stop control systems and so on. So, but given the amount of data that's generated by sensors, there has to be some intelligence in IoT embedded devices in order to process and make sense of that data and send a smaller amount of data to the cloud for decision making. So in that, the area of IoT in its broadest sense covers the areas of study right from interfacing with sensors at a very low level from these microcontroller chips, right through networking, so how the data can be efficiently communicated to the cloud for storage or for a decision to be made in the cloud and fed back to the device, and through the intelligence that needs to exist in the cloud in order to make sense of the data, which is what we call data analytics or data analysis. So IoT is very broad coverage in the electronics, computer architecture, and software space. So given this drive, this kind of unseen world that's kind of under the surface, the way that it's growing, there's an accelerating demand for engineers who have this broad skill set and can help companies move into this space or further develop IoT capabilities in the market. So that just gives you a broad picture of what IoT is and broadly what it involves. So specifically, then I want to relate the program coverage. So what modules are involved in DCIoT and how they cover this full kind of end-to-end domain that IoT spans. So the program covers right from sensors, low-level sensor interfacing through networks, all the way up to data analytics that would be done in the cloud. And the overall structure of GCIoT then contains 6 modules. So there are 5 EE, which are electronic engineering modules, plus there is one additional module, OI 501, which is what we would call a soft skills module, which is it takes a broader view of how the market is developing in this area and how you can shape your career to participate in the market and get maximum advantage of your knowledge. So then on the engineering modules, we have object-oriented programming with embedded systems. So this module covers Java and C++ right from the beginning. So if you're coming in to the program where you've maybe only taken 1 or 2 programming modules in the past, maybe C or something like that, this module will take you right from that point through modern high-level object-oriented programming languages, and also relate software development specifically to embedded systems. How do you write code for microcontrollers and for larger systems that surround them and interact with them? And then data analytics and machine learning is at the well, really spans the full gamut of IoT, in that sensor data in its raw form is of relatively little use until it is in some way aggregated or some sensor meaning is extracted from the data. So at the low level, data analysis and machine learning is important. And at the other end, when eventually the data is sent to the cloud to do something intelligent with data from multiple sensors, again, data analytics appears there. And this course covers from the beginning statistical methods through data analytics and machine learning. So there is some mathematical content. So if you have done maths modules in engineering or a science degree or a statistical numerical related degree, then that would be that is where this module would pick up on to develop it towards IoT applications. Then real-time digital signal processing and analysis, which we call DSP. So that entails hardware, specialized hardware systems for dealing with signals. So that's what we mean by DSP, FPGA, field programmable gate arrays. So these are specialized, high-speed, very efficient hardware that are where the hardware is essentially programmed or burnt into the device towards doing a very specific task. For example, to extract meaningful data out of complex sensor data, so that data can then be used to make decisions. Then connect embedded systems is a central module for this program. So that feeds on from object-oriented programming. It looks more into embedded system programming and the protocols around that allow you to interface with hardware and also communicate data to the cloud. So there has been a huge development in communications protocols recently that specialize or that are specifically targeted at enabling efficient communication between small systems, small embedded systems, and the cloud, and this module also deals with that. And then digging more into all things networks, network stack implementation, takes a broad view of networks and embedded systems, and systems that are running real-time operating systems, or TOS and Linux and so on. So that will cover TCP/IP, wireless protocols, and again specialized wireless protocols targeted at IoT. So I mentioned here, for example, 6LoWPAN, which is a very efficient protocol that can communicate, allow communication between microcontroller sensors and other systems at very, very low power. So a key constraint in developing these systems is the power constraints. Typically, we're talking about battery operated systems. We may not always be able to use Wi-Fi, which is relatively very high power in terms of battery use. So hopefully that gives you an idea of the coverage of the program broadly, and mentioning some specific programming languages that are covered, protocols and specific topics, and gives the idea that we are covering end-to-end IoT. It's not purely electronics or sensors, it's all the way through network protocols and data analytics as well. So the skills that are developed are very transferable and practical into even slightly other domains than IoT. And they're future-proofed fundamental skills at the same time. So they're not just targeted at an emerging IoT market that we don't know what shape it will have in maybe 5 or 10 years' time, but these fundamental skills will last a career and can be easily transferred into other domains. So to support that, all modules have a lot of practical assignments and projects, so you get hands-on experience with embedded systems and all of the topics that are covered in the course. So a little bit more about the details of the scheduling of the modules. So the program is a one-year program. It must be completed within 1 year. It's not possible to extend it into two. So we split into 2 semesters, semester 1 and 2. So semester 1 this year will begin Monday, October the 5th. It'll end Friday, December 11th. And in the first semester in this program, you'll take 3 modules, so OOP, data analysis, real-time signal processing. Then after that, there's an exam study period, and exams are in early January. So given the situation of COVID, exams will be what we call synchronous online exams. So these will be scheduled exams starting at a specific time, but you'll receive the exam paper materials online, and you'll submit your work, your script online after a certain time period. And then after that, there's a short break before the start of semester 2, which will run from around the end of January to mid-April. So we've yet to confirm exact dates. So in semester 2, you take connected embedded systems, which very much follows on from OOP in semester 1. Network stack implementation, and technology and ICT career success. So that module is 100% CA. It's actually spans semester 1 and 2, but most of the assessment is in semester 2. So again, after that, you have about a 2-week exam study period, and there are exams early mid-May. And then should you need to repeat any of the assessment for any of the modules, you can do so over the summer. You can repeat both the CA element over July and August, and you can, if needs be, you can repeat exams in the reset session in August. So in terms of the time commitment, so this is a level 9 graduate certificate. So you can expect, as with any graduate certificate, there is a significant amount of time required to be put into the modules to get through the program. So each module is what we call 7.5 European Credit Transfer System credits. So that's kind of a standardized unit of credit, which corresponds to a standardized amount of work in the ECTS system. So each module will total nominally about 190 hours total workload. So that is split up into somewhere between 30 and 40 contact hours. For lectures and tutorials. I'll say a little bit more about how they will be delivered a little in a minute. About 50 hours put into assignment work and projects, 50 hours into self-directed study, so studying materials from lectures each week and in preparation for doing your assignments, and then dedicated time at the end of semester to prep for the end of term exams. So what that would break down to per week for this program would nominally be about 40 hours per week. Now I say nominally because that really depends. That would really be at the high end if you were aiming for 80, 90% in every module. And if you had no prior experience in these topics and had to start everything kind of from scratch. So the modules are self-contained, and that's possible to do once you meet some basic prerequisites in your previous degrees, which I'll mention a little later. So for the typical student, it wouldn't necessarily be 40 hours a week, but you'd expect maybe 25 hours per week minimum. Okay, so that is still considered a part-time program. If you compare that to a full-time master's program, and those hours would look more like 60 hours nominal and close to 40 hours minimum. So it is still a part-time program, and we've had about 35 previous students on this program, and most of them were able to balance this workload with other workloads that they had. But it is a commitment in terms of time. Okay, to be aware of. So in terms of how we're going to deliver the program, so I've mentioned we've a lot of experience in delivering as an option programs remotely. So we've really just fallen into that mode for all students. For all our taught engineering programs, electronic engineering programs. So how this will work is lectures will be recorded, and they will be they'll be put up online each week. So there'll be a paced delivery of lectures. You'll have communications from the module coordinator, explaining what's being posted. So each week you can track progress through the material that's being presented. There will be some live sessions as well to keep an opportunity for students to interact with the lecturer live, ask questions, and to share questions amongst the class. That will also be supported by moderated discussion forums on what we call our Loop system. So Loop is essentially a version of Moodle, if you're familiar with that, virtual learning environment. So each module has its own Loop page where all materials are available, links to lecture recordings, to discussion fora, and everything is all aggregated and combined onto a Loop page for each module. DCU will have remote library access, and a large part of the library collection is available, particularly in our domain in electronics and computing, and a large part of it is available as electronic form books rather than printed material, printed books and journals. So there is direct support from module coordinators. So we don't have a system of teaching assistants. For example, all questions that you have go directly to the person coordinating the module, who are we're generally very, we're very responsive, particularly with online students, very responsive in replying to questions and queries. And then in terms of, so typically we would have had some on-campus labs, even for remote students. So they'd come in just for the occasional lab if it was hardware lab. We've thought very carefully about how we can continue to support the program fully online without with the same kind of lab experience, and we can do this for this program. If there's any hardware needed, which for this program will be things like electronic kit, sensors and so on, that will be provided. If any software licenses needed for any of the modules, such as MATLAB for DSP, are provided to students. The only exception I should mention is that the Connect Embedded module does require each student to have their own Raspberry Pi, but all the other electronics to interface with that for that module will be sent out to students. So we did do that in semester 2 for project students, and it worked very well. We had no problem, so we can continue the program as normal in this mode. So I know that often there's an interest from students on this program in the master's program and how you might continue after this program into the master's program. And the graduate certificate is specifically designed to allow students to easily transition onto the master's program. So we have a number of master's programs, and I'll briefly speak about them on the next slide. But in terms of what additional work you need to do to get a master's once you've completed the graduate certificate, 5 of the graduate certificate modules can be directly transferred onto the master's. So those 5 modules have actually been selected from 25 modules that we offer in the master's program. So those 5 would directly transfer, and then on the master's program, you just need to complete 3 further modules, taught modules from the master's program, 7.5 credit modules, plus a project. So the project is a large 30 credit project, which runs from the full year, from September, October until the end of December. Now, I should mention that although the graduate certificate is supported very generously by Springboard in terms of fees, if you did go on after this to do the master's, then you would have to pay those fees yourself. It's not part of the Springboard program. But you would have completed 5 of the 7.5 credit taught modules when you entered the program, and fees would not be charged for those. So you're charged on a modular basis in the master's program. On the master's program, we have 5 different majors options, and probably a particular interest if you're coming through the GCIOT route would be the major in Internet of Things, and maybe possibly image processing and analysis, because there's a strong connection between IoT and some of the topics you cover there, and what do you do in image processing and analysis. So I'll just speak very briefly then about what the master's program would look like. So the modules in green would be modules you'd have already completed on the grad cert, and you carry over to the master's. And so you would just need to take 3 optional modules. The core modules for this major on the master's you'd already have covered in the graduate certificate. So you can select from from about 20 different modules, remaining modules from the master's program to complete the program, the taught modules, and then do your project as well. It would also be possible to take 4 of your graduate certificate modules onto the image processing and analysis major. Then you'd have to do 4 taught modules in the project, but so you could convert from your graduate certificate, because we have very broad coverage of technologies, into other major areas afterwards as well. So just a note on the recognition of the program, given that we are in a different mode of teaching, particularly regarding assessment. So rather than having exam hall and invigilation exams, we have moved to synchronous online exams. So we're confident that this has not impacted at all how the program is viewed in terms of its standards. We have had discussions, for example, with Engineers Ireland, who are representative of industry in Ireland about this, and they understand what we're doing. And we have external examiners who have already looked at the semester 2 exam process, which was online, and they're very happy. We do our own analysis of results. We see no overall difference in how students are performing when we move to online exams. We are doing the exam at home rather than in an exam hall. So just to offer some reassurance, we have we have strong evidence and reassurance from industry that this will not impact how the mode of assessment will not impact how your award would be viewed in future. So finally then, some notes on applying. So I'm sure you have looked at the Springboard page, which has a lot of detail about the course content and how you apply. So all applications aren't directly to us, but they're through Springboard, and then they'll find their way to us. So this course on Springboard, the course code for Graduate Certificate in Internet of Things is DC839, and I've provided a direct link to the course there. So the deadline has been extended until the 11th of September, which is this day next week. So there is still a week to get applications in. A brief note on entry requirements. So an NFQ level 8 in electrical or electronic engineering, mechatronic engineering, physics, computing, or any degree that would have similar coverage to the topics you'd find on these degrees. So a level 8 is typically a 4-year degree, an honours bachelor. And given that many of the applicants are coming from industry with prior experience, we will certainly take account of that in terms of the entry requirements. So an NFQ level 7, which would be typically a 3-year degree program, plus a minimum of 3 years relevant experience that relates to the topics that you see here in the degree, but would also be acceptable for entry requirements. So we may interview candidates depending on just to if we need to understand a little bit about the background to make sure that we're sure that the course suits the applicant, and we're happy with they meet the entry requirements. So given that there's only a week left to apply, one hold up that you may have in applying is getting transcripts from your previous degree. And if you don't have them at hand and you request them, it might take a couple of weeks to get them from your last institution. So what you can do is go ahead and apply, supply what information you have, and we can, if we're happy with your application, we can make a conditional offer conditioned on you supplying the transcripts to us as soon as you can. Okay. So then a brief note on fees. So this program is heavily subsidised by Springboard. So the entire program fee, if you're currently in employment, is just €405. And if you're not currently in employment, it's free. So, so in comparison to, so €405 is just 10% of the full fee you pay for these modules. So it's a good opportunity to, I think, to do a program where cost at least is not one of the deciding factors. If you have any queries, if you have administrative queries, yeah, if you can please send them to Anya, who introduced this session today. So if that's anything to do with Springboard and the mechanics of applying or anything like that, Anya will be able to help you. If you have academic queries relating to, say, what prerequisites do I need, to be able to do this module or anything of that nature, please you can contact me directly. So as I mentioned, the prerequisites to keep in mind are some mathematical background is required for the data analytics module. This is an engineering program, so you expect it'll be founded on maths and science, and also some software experience by way of modules you've taken before, or practical experience is required, so that you can get a start into the more advanced software modules that are